Hey everyone, and welcome. Have you ever looked at two things that seem connected and wondered, wait, is that for real or is there something else going on behind the scenes? It's a huge problem in data analysis, and today we're going to crack it wide open using a tool called partial correlation, which is, believe it or not, way simpler than it sounds. I want you to imagine something. You're at a loud party, right? And you see two people talking, and you're trying to figure out if they're really connecting, if they're hitting it off. But the music is blaring, there are a dozen other conversations happening. How on earth do you isolate their specific conversation from all that other background noise? Well, that's exactly the challenge we're talking about today, just with data. And bam! This is what that challenge looks like in the world of statistics. I know, it looks super intimidating, right? Like some kind of secret code. But this little formula, the partial correlation coefficient, is our mission. And I promise you, by the end of this, it's going to seem incredibly straightforward. So, what does this code actually mean? All this R12.345 is asking is a really simple question, just dressed up in a fancy statistical outfit. It's asking, what's the true connection between variable 1 and variable 2, once we've totally filtered out the noise from variables 3, 4, and 5? Let's just break that down. X1 and X2. That's our conversation of interest. They're the two people we're leaning in to listen to. And X3, X4, and X5? Well, that's the crowd. That's all the background noise that might be making it look like X1 and X2 are connected, when really, it's just an illusion. Our job is to politely ask that crowd to be quiet. Okay, so how do we actually do that? How do we silence a statistical crowd? The strategy is, and I mean this, absolutely brilliant. Instead of trying to find the signal in the noise, we're actually going to capture all the noise first. And our secret weapon for doing that is a little technique called linear regression. Here's the game plan, and it's basically just two simple steps. First, we're going to use the crowd variables, X3, X4, and X5, to try and predict everything we possibly can about X1. Then, we're going to turn around and do the exact same thing for X2, using that very same crowd. So what this means is we're building two totally separate prediction machines. Machine number 1 gets fed all that crowd data, and its only job is to spit out the best possible guess for X1. Machine number 2 gets the same crowd data, but its job is to spit out a guess for X2, two separate missions. And this is what those prediction machines look like on paper. The top equation is learning the perfect recipe to combine X3, X4, and X5 to predict X1. The bottom one is doing the same for X2. And notice those little A's and B's? They're different, right? That's because each model is cooking up its own unique recipe for its specific target. But hang on. Look closer. See those E's at the very end? E1 and E2? Okay, that right there, that's not just some leftover math. That is the magic ticket. It is the entire key to solving this whole thing. So what in the world are these E terms? Well, they're basically everything our prediction machine got wrong. They're everything the crowd variables couldn't explain. They are the errors, the mistakes, or as we're going to call them, the leftovers. In statistics, the official term is residuals. Think of it like this. The residual for X1, which is E1, is the part of X1 that has absolutely nothing to do with the crowd's influence. We have statistically scrubbed it clean of any connection to X3, X4, and X5. It is the pure, unadulterated signal we've been trying to find all along. And you might think this is super complicated to calculate, but nope, it's literally just subtraction. For every single data point, we take the actual value we saw in the real world, and we subtract the predicted value that our model guessed. That difference, that's our leftover, that's our residual. And boom, that gives us E1. It's a whole list of numbers that represents the pure version of X1, with all that crowd noise totally filtered out. We've cleaned up our first variable. And you guessed it, we do the exact same thing for our second variable. We calculate E2 by taking the actual value of X2 and subtracting our second model's prediction. So now we have two clean lists of numbers, the leftovers from X1 and the leftovers from X2. All right, take a deep breath. We've done all the heavy lifting. We've built the models, we've filtered out all the noise, and we're left with the pure, unexplained essence of our two main variables. This brings us to the big reveal, the final, super satisfying step. So now we're just sitting here with these two lists of numbers. E1 is the clean version of X1. E2 is the clean version of X2. Both have had the influence of the crowd completely removed. So, what do you think we do now? Any guesses? It's almost ridiculously simple. We just correlate them. We take our list of E1 values and our list of E2 values, and we run a plain old, simple, standard correlation. That's it. That's the big secret. All that work was just to get our data ready for this one beautiful final step. So let's bring this all home. That scary-looking formula we started with, R12345, it turns out it's just a fancy way of saying the simple correlation between the leftovers of X1 and the leftovers of X2. It's incredible how breaking a problem down makes it so much simpler. And here's the really cool part. This isn't just a one-trick pony that solves this one specific problem. Oh no, this is a fundamental technique that you can use pretty much anywhere. And this is such a powerful idea once you really get this core logic. Regress, find the residuals, correlate the residuals. It's a tool you can always count on. It's not going to change on you. Are you controlling for 3 variables, or 30, or 100? It doesn't matter. The process is the same. Does the formula look totally different and confusing? Doesn't matter. The process underneath is always the same. It's like a statistical Swiss Army knife. Once you understand this one technique, you can solve all sorts of complicated problems. You've basically just learned a statistical superpower. So the next time you're digging into some data, don't just ask, hey, are these two things related? Ask the much smarter, much more powerful question. Are these two things related after I account for everything else that might be going on? You will be amazed at the true stories you can find hidden in the noise.